Okay, so we already took a look at how reactions can take place. From Chem 1, there's some rules if it is single replacement, double replacement, and so on. But that doesn't give us the whole picture if a reaction will take place or not. There's some theory around it, which is the collision theory background that we have to go through, which is going to allow us to go from, okay, what is happening at the microscopic level into a model that we can do some math calculations. And that is the Arrhenius equation that we are going to deal with towards the end. So you had all those chemical reactions. And the first part of today is, okay, looking at those factors that influence if the reaction will go faster or slower, or what needs to happen for that reaction to take place. And then we are going to add a couple of things that we did from Chem 1 when we did the Hess law and we did multiple reactions. We are going to take a look at that from a different perspective, and we are going to look at it, okay, do all reactions happen in one step, or are more than one step required for a reaction to happen? So we'll end up with that part. Is much easier than you think it's going to be. But let's start with this part just because it's the theory of all this. So for a chemical reaction to happen, at least three things need to happen. The first one is particles need to collide with each other. If I have a hydrogen standing here and an oxygen standing on the other side of the room, unless they hit each other, they're not going to form water. They need to collide with each other. So you need to have collisions, and there's some things that are going to affect if those collisions are going to happen or not. For example, the more particles you have, the more collisions you have, because the more chances for those particles to collide with each other. If you increase temperature, they will have enough energy to start moving and find each other and collide. So there's factors that can affect that collision. But that's not the whole thing. The other thing that needs to happen is that, yes, they need to collide, but they need to have the proper orientation. When you have the hydrogen and the water, they have to collide in a specific way so for that water to happen. When you put in a puzzle together, you have pieces that go in specific places because they need to fit the shape of that puzzle piece. The same thing happens in here. When you have the chemical reaction, those molecules need to fit specific locations. So they need to have that proper orientation. So that geometry that's going to form only forms if you can make and break bonds correctly. The last thing that needs to happen, and this is part of the Arrhenius equation, is that those reactions need to have enough energy for it to start happening. So there should be enough kinetic energy, which we are going to call activation energy, to break bonds so those bonds can form new bonds, so it can form new molecules. So the oxygen molecules and the hydrogen molecules, you can break those two hydrogens and those two oxygens so they can rearrange themselves and form water. So now we know, okay, I have a chemical reaction. Yes, I can have a single, a double, a synthesis, decomposition, but on top of that, they need to be able to collide. They need to be oriented in the correct way, and I need to have enough energy for that to happen. All that gets combined into an equation that we're going to take a look at in a little bit. So if we look at orientation a little further, it's like a lock and key mechanism. If it doesn't have the correct orientation, the reaction will not take place. Only when that orientation is perfect, that reaction takes place. And this is taken into account in the constant of the Arrhenius equation, which we'll see in a little bit. Okay. So when you have a reaction, you start with your reactants, you end with your products. And we are going to take a look at this with the second part of the lecture today, in which we will look at this diagram a little further. But when you have your reactants, you need enough energy so I can go over this transition state and make products. That transition state is where all that molecules are rearranging themselves. They are locking into the right position, and you make an intermediate complex. We'll look at that in a little bit again. But it's a transition state. So you need enough energy to go over that hump. And sometimes that energy is higher or lower depending on the factors affecting that chemical reaction. Do I have enough energy? Do I have enough temperature? Can I change how fast it can go? You already investigated a little bit of this when you did the online kinetics lab. So you can add like a catalyst, and then this hump becomes smaller and the reaction happens faster. So there are things that we can do to lower that activation energy. And we'll take a look at that as we go through. You want to have the lowest energy possible because that means that that reaction will happen faster, most likely will happen. The higher that energy, the harder for that reaction to happen, the more energy you have to put through for that reaction to happen. So we are looking at how big that activation energy is, and we are going to have some ways to be able to calculate what that activation energy is going to be. Okay, so I already mentioned, I can speed up the reaction by changing the temperature. By increasing temperature, I am lowering my activation energy because those molecules will have more energy to overcome that hump. So low temperatures, they need more energy to be able to get over the hump. Higher temperatures, I'm lowering the activation energy. So one way to lower activation energy, increasing temperature. That's the moral of the story in this graphic here. Now, again, this graph doesn't give you the whole picture. There's a little bit more that we have to add to this, but we are going to leave that for the second part of what we're doing today. Okay. So I already told you we have a way to do all this mathematically, and that is Arrhenius equation, where you have K equals A times E to the minus activation energy RT. The E is an exponential term. You have an activation energy EA. You have the gas constant. It has the units in here. So it has to be 8.314 joules per Kelvin. And temperature has to be in Kelvin. Don't forget, we had to, temperatures are usually in Kelvin on all the calculations we do in here, unless you are converting temperatures. So that K is a measure of the reaction speed. That A factor takes into account collisions and orientations. And then EA is just the activation energy for that reaction to take place. So we are not going to use this form of the equation. There's a different variation of the equation we are going to use. And depending which book you use, which resource you use, which AI you use, the equation will have a different look. So I already explained the A and the E factor. Not going over that again. So activation energy and this equation can be affected by temperature and the activation energy. If you increase the temperature, the K value increases and the exponent factor gets less negative. Basically, it speeds up the reaction. Having high activation energy slows down the reaction because it takes longer for that reaction to overcome that hump. So you want high temperature, low activation energy for those reactions to take place faster. So it's better to have low activation energy, higher temperatures. And I can see a question coming using these two factors. Okay. I don't want you to get too hung up with this lighting here, but I can take that Arrhenius equation and apply a linear manipulation where I can turn it into an equation of a line. And that is what we are going to use. Now, at the bottom of the slide, honestly, I don't care about how the manipulation takes place because it involves manipulating natural logs and exponentials. We are going to look at the final version of it, where natural log of K equals the activation energy over R times 1 over T plus natural log of A. We are going to manipulate that a little further to get the final version of the equation that I want you to remember. Again, we can plot some of the factors in that equation because it's a line. And we are going to end up with this equation that I have in here. The natural log of K1 over K2 equals the activation energy over R times 1 over T2 minus 1 over T1. And this is where, depending on the resource you use, this equation will look different. And you have to be careful because what happens is that sometimes, some authors flips the K2 and the K1, which makes the T2 and T1 to flip sides. So if K1 is on top, it's 1 over T2 minus over T1. If I have K2 over K1, it will be 1 over T1 minus 1 over T2. So it flips sides. So there's a couple variations to the same equations. Just want you to be careful which one you use. And like we've done in the past, K1 subscript 1 refers to condition 1. Subscript 2 reflects condition number 2. So I can give you at temperature 1, the rate constant is so much. If I change the temperature to this new value, what will the new rate be? So you can solve that equation for K2 in that case. Or if I have these two rate conditions, and I know that one of the temperatures, that you can solve for the other temperature. Or the third variation is I have all this information, what is the activation energy required for this reaction? Because it has 3 different variables, I can ask you for any of the 3 conditions. So what we are going to do, I'll go back to that slide, is we are going to look at an example. And I will work this on the board. So it says, if the rate constant K is 0.0014 at 25 degrees Celsius, and the activation energy is 40 kilojoules per mole, what is the rate constant at 50 degrees Celsius? So I'm giving you T1, so I had to convert that to kelvins by adding 273. The same with T2. I had the activation energy, it's in kilojoules, I had to convert that to joules. So I had to multiply by 1,000 to be able to do that. I don't know K1 because that's what I'm looking for. K1 is known, so that's given in the problem. K2 is the one that I need to find at 50 degrees Celsius. So as you read the problem, The giveaway in here, okay, what equation will I need to use? It's giving you activation energy, so you need to know it's Arrhenius equation. Find those key words. They will tell you what equation you need, and then list what you have. You need to be able to be good at pairing conditions together. So you have K1, T1, you have T2, but you don't have K2, so you have to solve for that K2. So we already know we need a Arrhenius equation. So I am going to write that down. So that's the version of the equation. Natural log of K1 over K2 equals activation energy over R times 1 over T2 minus over T1. I am going to substitute everything that I have. Once I substitute everything that I have, I'm going to simplify just to make things easier. One thing I want you to be careful with, when you're dealing with natural logs and exponentials, those negative signs do have an effect on the answer. So make sure you add those in your calculations. Don't forget them or put them in the wrong location because they will change the answer magnitude. So I can still simplify this a little more. Hold on, that's wrong. To take that natural log out of the way on the left side, I have to take the exponential of the number on the other side. That's a math property. And when you take the exponential of minus 1.2495, you get a 0.2866. And the case have second minus 1 units because my K1 is second minus 1, so my K2 is also going to be seconds minus 1. Okay. Yes. To go for the natural log, to get rid of it, I took the exponential of the number on the other side. I'm going to leave that there for a little bit so you can catch up. One way you can check your answer is that, okay, my temperature went up, so my rate should go up as well. And that is what happened. So the temperature increased, the rate increased, so the result is logical, makes sense. I will go with that. In your homework, I think you have a couple problems that deal with Arrhenius equation. Again, you are looking for the problem to state, calculate the activation energy or the activation energy is, and that's the giveaway for Arrhenius equation. So to summarize what we just did, you have the physics of all this, which is the particles have to collide, they have to have the right orientation, the right energy. We took all that information and put it into an equation that we can use to do some type of calculations and make predictions. And that is your Arrhenius equation. And those factors that I just mentioned are embedded into the A and the EA aspects of the equation, just making sure that when you write that Arrhenius equation, you stick with the version where the variables are placed in the correct position and you don't flip the variables, especially the temperatures where they shouldn't, and make sure you carry out the negative signs when you have to, because those do have an effect in your answer. I can take that equation. If I wanted, I can give you a lot of data. You can plot it, and you can plot the natural log of K versus 1 over T. It's a straight line where the slope is the activation energy. And we are going to leave that topic on Arrhenius equations there. That's the last of this part.